Let's begin. All right. I wanted to follow up on something we decided to do as a homework assignment last time, which had to do with the stability of the advection-diffusion with upwind scheme. I decided otherwise. I decided that I want to share with you that stability derivation, and you'll still have something to do with the homework assignment. But because I need to introduce the Courant number and its importance in advection. So I will go back to the advection equation with the upwind scheme. So remember, advection was central. FTCS on advection was unconditionally unstable, and we showed that with that simple moving of a single pulse. Then we did upwinding, and we demonstrated that for some time steps it works, for some others it doesn't. So at least there's a range of time steps where the scheme is stable and bounded. And we also noted that it's diffusive. It diffuses the signal. That's what you will demonstrate in your homework assignment. But today I want to talk about the stability. Last week we said we'll keep stability for the homework assignment. I think I want to do it today. And I will consider that same situation where you have this grid arrangement, zeros everywhere, and just a single value at some node in the middle of the domain. And remember, this was our upwind scheme on the advection equation with flow moving from left to right. So see that advection speed is positive. So flow is moving from left to right on this problem. Now, this number, C delta t over delta x, is a dimensionless quantity. It's called the Courant number. If you look at it, C is speed, meter per second, times second. So that's meter over meter, makes it dimensionless. And it is actually a measure of how much information you can move in a single time step at a speed c. So if you have information moving at speed c, you choose your time step delta t. It's a measure of how many delta x's are you moving that information. If c delta t, or if this number is greater than 1, then you're moving the information more than one grid point at a time. Right? So essentially, it's the fraction of the grid resolution through which you're moving information. Okay? That's very important. Okay. So if you write it in terms of the Courant number, call that beta for some reason, you get this simpler version of that equation, this condensed version of that equation. Okay. So for the advection equation, we expect things to move. Okay, if speed is positive, things should move from left to right, as in this arrangement. And also, should not go negative. Okay, should not go negative. All right, so let's take a single time step and see what happens according to this equation. So if you had that situation, zeros and 1, and you're going to apply this scheme at every point. So you go to this point, it's beta ui minus 1n, which is 0. So this is at this point is 0. This one, what's going to happen in a single time step is going to be 1 minus beta, and the next point is going to be beta. So what happened, we did move things a little bit to the right. So now instead of 0, we have beta. Instead of 1 here, we have 1 minus beta. Okay, so we are kind of on the right track. Okay, but now you can say, if you want things to be bounded and correct, beta, this motion can never be negative. So that puts a bound on beta, that if you want this to never be negative, beta needs to be less than 1. Okay. And over here as well, if beta is less than 1, then you're making sure that you're not kind of blowing things out of proportion. And indeed, that condition, if we satisfy that condition, then our solution can proceed. So in other words, this says that your Courant number needs to be less than 1. Now, when you think about it physically, what you're saying is, in an explicit method, you cannot move information more than one grid point at a time. And that makes sense, right? If you put your Courant number at 2, you choose delta t, so your Courant number is 2. You're trying to move over a grid point. And like, how do you transmit information? Are you going through a black hole or something to get through to the other point? You have to go through each and every grid point to move information along. you cannot bypass, it's illegal to bypass any grid point. That's what this condition is saying. You can move less than one grid point at a time. That's okay. You can bring in information a little bit at a time. As long as that you're satisfying that, you're good to go and you're stable. This condition is called the CFL condition, named after Richard Courant, who was the behind this number, 1928 paper. Courant, Friedrichs, and Louis condition. So CFL condition, you've heard of that. Okay. Now, don't call this the CFL number. CFL is not a number, it's a condition. This is the CFL condition. The CFL condition is a condition on the Courant number. Okay. Now, some people might say, well, they tell you, okay, what Courant number are you running your simulation at? Oh, you say my Courant number is 0.5. So what that means that this condition is less than 0.5 or equal to 0.5, right? So that's kind of how you think about it. In other words, you're only moving half a grid point. You're moving the information at most half a grid point at a time. Okay? I'm moving very slowly then. Okay, so I just wanted to cover that and bring in the Courant number. In your homework assignment, I think as I planned the homework assignment, I will want you to demonstrate two things. One of them is, why do you get diffusion with this upwind scheme? And you kind of can tell, because one now is no longer, if this is true advection, this should be 0 and this should be 1. And then on the next step, this would be 0 and this would, you're moving that number 1 through each grid point at every time step, okay? But apparently this is not the case here, okay? So, you know, you have to demonstrate why there's going to be a diffusion term with a modified equation. Okay, so we're done with that. Now I'm going to catch up with where we left off last time with the advection-diffusion equation. And we did the coding, and we will revisit this coding next Tuesday as we prep for Navier-Stokes. So I'm not going to do coding on advection-diffusion. I'll share these slides with you at the end. I have to update them. They're on Canvas. I've changed a lot of stuff on the slides. So I'll update them tonight and share them again. Yes?
So at the end of last class, you had said that there was an issue with the ghost cells, or the way it was, the periodicity. It was causing some issues.
Yeah, so we just choose a different frequency. We just had to choose a different frequency for the function, because that function was periodic. So choose the domain either to be, choose your domain 0 to 1, for example, and choose your frequency 2 pi. Or choose your domain to be 2 pi and your frequency as a wave number, 2, 3, or 4. Just a multiple of pi. That will fix it. That will fix things. And then you can compare with the analytical solution. But it's still a legitimate solution, though. It's not, we won't be able to compare it to this analytical solution. Okay? So you just have to choose your function so that you are satisfying correct periodicity at the endpoints. Okay? That's all there was. Anyway, so we covered that last time, and we said that we were going to use central on advection, and the argument was, although central on advection was unconditionally unstable, we do have diffusion. And diffusion was so very effective. If you're working on your homework, it's very effective at diffusing high-frequency signals. And if you remember what happened with FTCS on advection, we had a lot of these very high-frequency modes show up because of the error just kind of blowing up. So diffusion is able to suppress those, physical diffusion. Okay? All right, so here are some examples of the code we did together and trying to compare this with the analytical solution for different time steps and different grid resolutions. So this is delta t 0.05. Obviously, it's unstable. The blue dots are my numerical solution. The black line is the analytical solution. This one we get a little bit more stable, and even so more stable, more grid resolution. So this should be 21 points. This is, yeah, this should be a smaller time step size. So more and more resolved, and eventually here like 10 to the minus 5 time step and 201 grid points, and you see we can get pretty accurate compared to the analytical solution. Okay, and so we can get as accurate as we like, but still we don't have guideline here over the time step size. I want to summarize what we did so far. Okay, let me just fix this animation here for a second, please. Appear by bullet point. Okay, so what have we learned so far? This is a very useful slide. We learned that the advection diffusion is a great model or toy problem to study and learn numerical methods for Navier-Stokes. Why? It's simple, it's linear, we can compare with analytical solutions, it's easy to manipulate, right? There's no crazy nonlinear terms, everything is nice and clean. Okay, so it's a great toy model for Navier-Stokes. We learned how to discretize the 1D steady state diffusion, the Poisson equation, 1D unsteady advection, unsteady diffusion, and advection-diffusion equations, all in 1D. We learned how to do that. We learned that the FTCS scheme, forward in time, central in space, on the diffusion equation is stable for Fourier numbers less than half. And we also learned that diffusion is very effective at eliminating high-frequency signals. Good. We learned that the FTCS scheme on the advection equation is unconditionally unstable. There's no time step size that could result in a stable calculation because the scheme results in negative diffusion from the modified equation. So let me add this. We learned okay, so let me go back, just adding a couple of terms here. So these are like your flashcards. So with that scheme, the FTCS on advection, we learned about the modified equation, which is the true continuous PDE that solves that the discrete equation is actually solving. Because when you discretize a model equation, you truncate the error. That discrete equation is only an approximation to that true equation, but the modified equation tells us what the true equation is that this discrete equation is solving. So by tracking all the truncation error. And we showed with that, with the modified equation, that the FTCS on advection is unconditionally unstable because it results in negative diffusion. Negative diffusion is making things out of nothing, essentially, making large things larger and small things smaller. So it results in this unbounded growth. And we showed that FTCS on advection resulted in these high-frequency errors that grew unbounded. Then we learned about the FTUS scheme, which is upwind, forward in time upwind on advection. And that is stable, today we learned, when the Courant number is less than 1. So now you can go back to your code, and you've chosen delta x, you've chosen your speed, then you can calculate a stable delta t from that combination by making sure that your Courant number is less than 1. I use 0.99, for example, or 0.95, okay? However, we also noticed that FTUS on advection is diffusive. It makes the signal, we started with this Gaussian signal, and then it started kind of flattening out. So it is diffusive. And we say this is artificial diffusion or numerical diffusion. So that numerical approximation for the advection equation somehow is producing artificial diffusion. Hint, hint, we can demonstrate that from the modified equation, which is what you will do in your homework assignment, I think. The FTCS scheme on the advection-diffusion equation can be stable, as we showed last Tuesday, despite using central scheme on advection, because diffusion is able to stabilize high-frequency errors. Speaking of errors, given an analytical solution, we can compute a pointwise error of our numerical calculation. Okay? You don't have to do this for your homework assignment, because here what I'm driving this here is to really compute convergence rates, or the leading order term in the truncation error. But you can use this approach if you want. So in general, you can just take the exact solution and subtract from it the numerical solution at every time step. That gives you an error at every point, right? It's kind of obvious. Now, you can define an error norm, or in other words, a summary of that error on your calculation. So, you know, on a one-dimensional grid, you have 100 points, you have 100 errors. What is your error? You know, we need one number to say, oh, my error on average, or some measure of the total error that represents the error on the domain. You can say, I want to pick the worst point. Yeah, you can take the maximum error, okay? Or you want to compute an average Pythagorean error, the square root of the sum of all the errors squared, right? Some measure of the error. These are called error norms, and typically 3 error norms that we use in computational fluid dynamics are the L1, L2, and L infinity error norms. And simply, so if you have a pointwise errors on your grid, the L1 norm is simply the sum of all of those errors. Okay, in absolute value, you can add an absolute value. You should add an absolute value. So here should be an absolute value. Now notice I'm scaling this with delta x. In your homework, you will show why you need to scale this with delta x, because these norms actually come from vector spaces. This is the result of the integral of E dx. And when you approximate that, you need that delta x scaling. Otherwise, you can never demonstrate convergence rates correctly. You will show that, and I will guide you in your homework assignments on how to do that. With the L2 error norm, this is the Pythagorean norm, and it's defined as the square root of delta x, your grid spacing, times the summation of your errors squared. Okay? So that's like it's measuring length. C squared is a squared plus b squared, or C is equal to the square root of a squared plus b squared. So you take all the squares of the error, sum them up, take their square root, and you have to scale by this delta x. The L infinity norm, or the worst error, like I said, you could choose, say, you know, I want to pick the worst error, is simply the maximum error in your domain. Okay, take that maximum error. Okay. Now, why I need this is to measure. If I have an analytical solution and a numerical solution, I can use this fact to measure my actual truncation error. Is it true that I have a second order approximation in space for diffusion and a first order in time for, you know, my solution? Like as I change things in time or I change my resolution in space, does my error reduce accordingly? So for example, a second order scheme or a first order scheme, if you double the resolution, you cut the error by half. A second order scheme, you cut it by a fourth, right? So that's something that would be very important, like we discussed early in the beginning. Yes?
Why do you need to multiply with del x?
You will prove that in your homework assignment. Yeah, because now these error norms actually come from vector space calculus. So this is an approximation of the true definition of the norm, which is the integral of the square root of e squared times dx. And that, when you approximate that integral, what do you do with dx? It becomes a delta x. If you don't include that, you cannot get good convergence. You cannot get appropriate convergence rates. So if you're doing some numerical work, don't forget to scale correctly. This is not just the summation over, you know, or the average number of points. It might work for the average number of points sometimes if you're like if your grid resolution is not consistent, you have to have a delta xi here. You have to add up each term and scale it by the appropriate delta x to get correct convergence rates. Okay? So, but in your homework assignment, you'll do some math and show that yes, I need to do the correct scaling to show that I can converge at the correct rate if you do this scaling. Okay, so we can examine both spatial and temporal errors to see if our code is actually converging at the expected rate. Okay, and don't forget to do the delta x scaling in these norms. So how do we do this? To examine spatial errors, we pick a very small time step and then refine our grid spacing. We're not going to do this in class. I'm not going to ask you about this. We're just giving you an idea of how it's done to show convergence rates. So with the spatial error, you're testing sensitivity over grid spacing. So if you fix your time step, remember, your total truncation error consists of temporal errors and spatial errors, and sometimes they're multiplied together. So what you do to examine only spatial error, you need to hold your temporal error fixed. Okay? So you pick a very small time step, hoping that your temporal error is smaller than your spatial error, and then you refine in space. You double your resolution, you quadruple it, etc., and then you see how the error changes as you refine your grid resolution. So you solve the same problem at the same time step, but at different grid points. You start with 100 grid points, 200, 400, 800, and calculate the error at each step and report it. Okay? And you do the same thing with temporal errors. Temporal errors are a little bit more tricky because you have to run them to a fixed end time. You have to run, if in your first calculation you run a single time step, the second one you cut it in half, you run 2 time steps, so you need to end at the same time. You need to run to run as many timestamps until you end at the same time. I give an example code over here. You can copy and paste it, and for the advection-diffusion problem. And what I'm testing here is spatial error, and I'm looking at the advection-diffusion equation with central scheme. So I expect a second-order convergence rate. In other words, my error needs to be cut by a fourth. Okay. So in a log-log plot, these would look like as straight lines. This would be the straight line for a first-order error. This would be the line for a second-order error. And these are my errors. So I'm taking the analytical solution. You see here, u exact minus u numerical. And I'm taking their norm and multiplying by delta x. Okay? And then I plot the error simply on the log-log plot. And it is exactly parallel. So the slope is what matters. Here, it is exactly parallel to this line. Okay? It converges as I refine in space. So the axis here, this is the error value, the value of the error norm, and this is the number of grid points. So as I put more grid points, my error is decreasing according to second order accuracy. Okay, but then something happens here. I go flat. Can you explain this? Okay, what do you call that? So our error, in every calculation that you do, there is round-off errors. These are errors whenever you put in real numbers on a computer, called round-off. Okay? At this point here, our truncation error is so small, it's actually smaller than round-off. Round-off doesn't have a convergence rate. Okay? Sometimes you see this go up or oscillate. It's just round-off. So you've reached the limit of what your computer can actually do. This computer, if I run the same code on your computer, we might hit it lower, or we might hit it sooner. Okay, because round-off is different on different machines, depends on the processor, etc. But at least I know that in some range I can converge at the correct order. Okay, I'm not gonna drag you through a lot of spatial and temporal error analysis. If you're interested, we can do this later in the course if you have some projects that you're working on. I mean, this could be pedantic. It's important. We do it a lot in our work, like ask Maher. All like half of the plots in his papers are just these straight line plots. Yes?
But this would be good for verification and validation.
Absolutely, 100%. This would be very important for that, 100%. And you can do it actually without an analytical solution. You can do successive refinements. So you run a very, very fine resolution calculation and treat that as the truth. And then relatively, you can take the difference. You do it carefully, you can get this right. But it's a different topic than what I'm interested in doing here today. We can, if you guys are interested, we can revisit it later, okay? Okay, as long as accuracy is reasonable, then integration at larger time steps is desirable and more efficient, right? So if you're happy with your accuracy, yeah, just move on with life. There's no reason to take smaller time steps. However, as we saw earlier, different schemes combined with different equations, you can't just take arbitrarily large time steps, especially for explicit methods. Explicit methods are nice, easy to implement, they're efficient, they're highly parallelizable on big supercomputers, they're scalable, but they suffer from time step limitations. So you cannot take an arbitrarily large time step. And that is due to stability. So we are going to define naive stability, or the simplest meaning of stability, as your solution is not blowing up, right? So we're gonna define stability as instability as a solution that oscillates or that grows unbounded. Okay, it could oscillate and stay bounded. That might be acceptable to you. Okay, might be acceptable to you as long as it's bounded. Okay, but stability in the simple sense is when errors from round-off and or truncation do not grow indefinitely. So if you recall the FTCS scheme on advection, we started seeing growth. That is coming from the truncation error. Okay, that is coming from the truncation error. In some other schemes, you're going to see some errors show up, okay, which might lead to instability. Okay, so we define stability as the ratio of the error or the value at the new time step over the previous time step. It should not be unbounded. It should be less than or equal to 1. Now, you might say, well, what if you have a process that actually is adding, is a source term, etc., to the problem? We're not interested in that situation, because even with a source term, you can still have an entirely physical process. What we're interested in is taking the simplest equation where you expect decay, for example, diffusion. In that situation, does the numerical scheme cause unbounded growth? If it works on that process, then it should work on the other one with a source term that could be increasing the solution physically. Right? A solution can grow physically. If physically you're adding things to the solution, that's fine. Right? But that's not what stability is addressing. Stability is talking about a process. If it's decaying, it should decay. If it's moving, like advection, it should be moving. It shouldn't just blow up. Right? Do you have a? Okay. Okay. So let's start with a simple example on ordinary differential equations. I'm going to take this simple equation, u prime equal minus u, with an initial condition of 1. So t equals 0 equal 1. We know the exact solution is simply exponential decay, e to the minus t. Okay, so that's the exact solution for this problem. Okay, so we expect, so this is a model equation where I know that my solution should decay over time. So my numerical method, therefore, should capture that behavior. All right, so it's a great example problem. So this would mimic diffusion, for example, decay with diffusion. All right, so if we take our forward Euler scheme, it says un plus 1 is un minus delta t times the right-hand side at n, which is un. So you get 1 minus delta t times un. Okay, great. Now simply, what I expect from this problem is for things to decay, for the new value of u to be less than the old value of u. So I want, really, literally, that stability condition, un plus 1, to be less than un in the absolute value sense, okay? Or in other words, un plus 1 over un in absolute value to be less than 1. Now, what is un plus 1 over un? It's simply 1 minus delta t. So I want the absolute value of 1 minus delta t to be less than 1 or equal to 1. It gives you two conditions. The most loose condition is that delta t is less than or equal to 2. It is positive, so you know that condition we are satisfied. So we know that for delta t less than or equal to 2, we get a stable solution. Stable. Well, look what happens. What I'm plotting here is the value of u versus time, looking at the exact solution, which is in blue, and showing my numerical solution at different time steps. At dt equals 0.5 in orange, we know that this satisfies this condition. It is indeed stable. Look at that. Goes on. At dt equal 2.1, which is greater than, which violates this condition, you see this red line, they're starting to grow, right? So you get this unbounded oscillatory growth. Okay, that's exactly what we're looking at about stability. Now in green, I have an interesting situation. For delta t equal 1.5, the solution is stable, but is oscillatory. It oscillates negative, positive, but then it dampens out. That's what I mean by stability. If there is some error, something weird going on, it's going to be suppressed very quickly. Now, obviously, that delta t size, 1.5, is really not acceptable because I still don't want it to be oscillatory. But that's a stricter condition on the solution. When we talk about stability, is that it doesn't blow up. It might be oscillatory, but it doesn't blow up. So that's how we're going to proceed. Now, for this case, there's a simple solution to figure this out, what time step size to be not oscillatory. So if you were to take that equation, un plus 1 equal 1 minus delta t un, and you go back in time recursively to u0. So you say, OK, 1 minus delta t un, but un is 1 minus delta t un minus 1. So you get minus delta t squared un minus 1. All the way to u0, you get un plus 1 is 1 minus delta t to the power n times u0, your initial condition. N is an integer. So this is 1 minus epsilon, or 1 minus delta t to the power n. If that number is negative, then it's going to oscillate if n is odd or even. Right? That's why you see that oscillation. So although if delta t is less than 2, it's stable because it is going to be less than 1, right? but it's going to oscillate. So the best way to avoid these oscillations is if delta t is less than 1, actually, which is a stronger, stricter condition in that case, right? If delta t is less than 1, then this argument here is always positive, and it's not affected by whether this is odd or even. If delta t is greater than 1 but less than 2, then this number is negative. And it's going to be positive if n is even, negative if n is odd. And so that's why you see these oscillations, right? Time step 1, it's negative. Time step 2, it's positive. Time step, the green one. Time step 2 is positive. 3 is negative, 2, and so on. That's why you see that, okay? Okay. Now, can we do this for partial differential equations? That's what we're after. So we have the Fourier condition on diffusion. We have the Courant number on advection, but we don't have a condition on advection-diffusion, right? So last time we were just randomly scrambling for a delta t. Okay, could we have a condition for stability for advection-diffusion? Yes, but it's going to take a little bit more work. It is very difficult in general to do insightful or useful stability analysis on linear PDEs. It's even worse for nonlinear PDEs, okay? But still, we can gain some insight from the linear PDEs in one dimension, and it's very tedious work, but it's doable, and people have done it, and we're going to do an example today, and you'll do one in your homework as well. Man, that's a lot of homework. Yeah, I was told that the homework in CFD is kind of lengthy. Anyway, okay. So it's very hard, but it's doable. That's why we picked the advection-diffusion equation, because it's linear, and this stability analysis is very effective on these linear PDEs. There's like matrix methods and other eigenvalue methods. We're not going to get into any of those. We can talk about them later, but I want to get you to do a CFD problem. Okay, so we're just getting the pieces that are necessary to get to that point. So one useful procedure to get stability for these linear PDEs is what we call the von Neumann stability analysis, after the mathematician John von Neumann. And we will consider here, this is just an example, we will consider the FTCS scheme on advection. Okay, so central in space for advection, right, forward in time. And we know that that scheme is unconditionally unstable. So I want to prove that it's unconditionally unstable using math, using this method by von Neumann. And similar to what we did with the ODE, von Neumann said, hey, let's look at the amplification of the solution. So un plus 1 over un. But in this form, there is no way we can simplify this, because this is at I plus 1 and I minus 1. Right, so if we divide by uin plus 1 over uin, there's no way I can get rid of these terms. And if you expand them in Taylor series, it doesn't give you any answer. So we actually need to go to wave space, where in wave space, you invert your derivatives become algebraic relations. It simplifies things a lot. And think about it the way von Neumann thought about it, I think, or we think, like Newton's apple, we think that's what happened. We think with von Neumann, he said, you know what if some error signal showed up? Now you can imagine a single pulse, like the example I showed you. In real space, it's simple. It's zeros and 1 and zeros. If you write the Fourier series of that pulse, it's thousands of Fourier modes just to get 0, 1, and then 0. So you can imagine something as benign as that single value showing up at a grid point is actually the superposition of hundreds of thousands of frequencies and waves. So von Neumann said, what if one of those frequencies showed up? Is it going to grow or is it going to dissipate? So let's go ahead and express our solution as a Fourier transform, as a discrete Fourier transform. And he said, let the solution, and this is mathematically valid. It's not an approximation. This is true mathematically. He said, let our solution at point I or j at time n, look like a summation of an infinite number of Fourier modes. You see here a coefficient which changes in time, and then a wave signal here. So the I allows you to combine sines and cosines, sines and cosines together in a single term. So this strictly represents the signal in space, okay? By changing the k, which is the wave number. So wave number 1, you get first frequency. Wave number 2, you get, you know, second frequency, third frequency, and so on and so forth, okay? Now, because this equation is linear, we don't need the summation anymore. All we need is to look at one mode, one frequency, whatever that frequency is. Because that summation that equation is going to be valid to each and every mode in that summation, right? So if you substitute this over there, this will be true for each mode individually, because that equation is linear. There's no nonlinearity. There's no multiplication of these exponentials or summations together. This will result in the summation of this entire PDE, which is then what you care about. You don't care about the summation anymore. You just care about what's inside that summation. Okay, now because the summation it is linear, you can drop the summation, and then you look at a single arbitrary frequency. We don't know what the frequency is, and it shouldn't matter because the solution should be independent of that frequency. Any frequency, if it's going to blow up, it's just going to blow up. It might blow up faster than the other, but it will blow up. So this analysis will show that. So then we drop the summation, and then we assume that UIN is some coefficient times n at time n times some frequency in space. Okay, and then this is what's neat about this exponential Fourier form. U at I plus 1 or j plus 1 is simply at xi plus delta x, and then you can split that as a product in the exponential. So now what will happen, I can tie in ui plus 1 to ui by this e to the ikxj, ikxj, and those will cancel out. See what I'm doing here? I'm trying to tie in ui plus 1 and ui minus 1 to ui so we can divide everything un plus 1 over un, right? And same thing for the left grid point, ui minus 1. Just simply substitute at I minus 1. So this would be xi minus 1, which is xi minus delta x. And you get this. Just simple algebra. Nothing fancy here. Just simple algebra. OK. So we take those and simply substitute them back into our numerical solution. OK. So this becomes epsilon n plus 1 e to the ikx. OK. And this is epsilon n e to the ikx minus Courant number over 2. Epsilon n e to the ikx e to the ik delta x. Epsilon n e to the ikx e to the minus ik delta x. Now, you see how ui plus 1, ui minus 1, we were able to extract ui from them, right? So we can cancel them out. Very beautiful. OK. So now let's cancel out to the e to the ikx. Okay? And then we finally get this really neat formula. Epsilon n plus 1, epsilon n, epsilon, epsilon n. Bingo. We can divide by epsilon n. Remember, we're looking at the growth in time. So un plus 1 over un is nothing more than epsilon n plus 1 over epsilon n, because everything else went to the right-hand side. OK? OK, great. So let's take this now and divide by epsilon n. So when you divide by epsilon n, you get this ratio, which is similar to un plus 1 over un, okay? Which is exactly equal to un plus 1 over un, actually, which is equal to minus c delta t, this term. You might say, oh, this is great. This amplification is going to be less than 1 because this is 1 minus something. No, 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 no. This is complex space. This is not a number. This is a weird number. This goes in another dimension. OK? So we can't look at this. We're not there yet. We need to take the magnitude of this. So let's see how this works. I'm going to simplify this with one more combination by taking the sine rule for the exponential, and this combo becomes I sine k delta x. Now, why this is useful? Because I know sine, the sine function, is always bounded between minus 1 and 1. Okay, so this is nice, regardless of the frequency and delta x. Sine something is always between minus 1 and 1. So I can reason about it. Okay? Okay? Literally, every von Neumann stability analysis looks like this. You take the exponentials, try to get a sine or a cosine, and then look at the next step. Now, we say that the method is stable. Now, we agree that this ratio of these signals at the new time over the old time represents a measure of growth. If this ratio somehow is greater than 1, then it's going to blow up. If it's less, then it's not going to blow up. Now, because this is a complex number, what we need to look at is the magnitude of that number. So this is just a complex number. There's this I, right? Then we say that the method is stable if g of k, k is that frequency signal, which is the magnitude of this ratio. Now, this is complex number magnitude, okay? So which is the square root of a squared plus b squared, complex numbers, is less than 1, okay? So you look at g squared. So if you think of this complex number as a plus ib, then the magnitude squared is a squared plus b squared. Then you get this. Now this changes everything. We thought we had a negative sign. Remember, FTCS on advection is unconditionally unstable. So we expect g to be greater than 1. And indeed, g squared is greater than 1. You take g, which is simply the square root. It's always greater than 1, greater than equal to 1. And that's why that scheme is unstable. So what this process does, the von Neumann analysis, it says, hey, dude, we're going to take this discrete equation. We're going to shove a signal through it. What happens to that signal? Is it going to grow or is it going to shrink over time? If g is greater than 1, it's going to grow. Very simple. Take any discrete equation, apply that same analysis. Assume a signal, epsilon n e to the I k x. It doesn't matter what k is. It's insignificant. K and delta x and those are insignificant because they just don't matter, right? Yes? It's a wave number, yeah, which is correlated with the frequency. So that summation could represent any initial condition, for example, right? But you don't need all of that. All you need is just one frequency, one frequency. We're going to come back to this representation later to study numerical diffusion and dispersion and other things. And then we'll give more concrete examples of this. Okay. All right, so in your homework, I think you will derive the stability, this analysis for the FTUS scheme on advection. So we're going to do upwinding. And then you'll demonstrate, you'll derive the Courant number condition with this approach. So you will have something here, and you will say, oh, when the Courant number is less than 1, then g of k is going to be less than 1. Okay. Now, advection-diffusion equation, nasty problem. I'm going to do it for you. Okay, I'll just share with you the result. So it's been published over and over and over again. And in 2022, I wrote a paper with one of my former students, Mokbel, and we kind of summarized what's in the literature and derived everything in a different way, and we showed results for previously unknown cases like Runge-Kutta 2, 3, and 4th order methods in time. So what happens for the advection-diffusion equation is you will get two conditions with FTCS. You need to satisfy two conditions, okay? So I'll remind you that the Courant number is defined as u times delta t over delta x, and what is going to follow in these slides is the absolute value of the speed times delta t over delta x. And I'm going to introduce another number called the Peclet number, which is just the Cell-Reynolds number. It's u delta x over mu. If you remember the Reynolds number, rho vd over mu. So it's just a Cell-Reynolds number if you want. It measures the inertia over diffusion, okay? Strengths of inertia over diffusion, or advection over diffusion. Which is stronger? Are you advecting faster than you're diffusing? That's what it measures. And they're both tied into the Fourier number, which we showed earlier, Courant, the Fourier number less than 1/2 for the diffusion FTCS. It's the Fourier number is the Courant number over the Peclet number. So keep this in mind, because I'm going to present everything in terms of the Courant and Peclet numbers. Okay, so for the FTCS on the advection diffusion, you will have two rules, rule 1, rule 2. And I'm going to show them in 1D, 2D, and 3 dimensions. Okay? Are you ready? Okay. The first rule, which is kind of like well known, And the second rule is Courant over Peclet less than half, and Courant times Peclet less than 2. So you need to satisfy both of those conditions to pick the smallest delta t. I'll show you how in a second what the procedure is. Now it's interesting when you go to 2 dimensions, it becomes a summation. You have to do the Courant in the x direction over Peclet in x, Courant in y and Peclet in y, less than 2, plus. And then Courant x, Peclet x plus Courant y times Peclet y less than 2. And finally, in 3D, same procedure applies. But you might say, like, how is this going to work if I have like a 2-dimensional grid with different speeds and different diffusion coefficients? Piece of cake. Here's how you do this. For each grid point, you visit each grid point, and you get a delta t from each rule. Remember, there's only one delta t here from Courant and one delta t from Courant here. If you have your grid resolution at that point, you have your delta x, you have delta y, you have your delta z, you have your diffusion coefficient, you have your local velocity at point I, which are numbers that exist on your grid. You can extract a delta t. Okay, so you get a delta t from this rule that satisfies this rule, and a delta t that satisfies that rule. Okay, at each grid point. Then you take the minimum of those 2 delta t's. Remember, we're going to pick the worst case scenario, and we're going to take the most conservative delta t. So you take those 2 delta t's at each grid point, okay, and you take their minimum. So now you have a small delta t at each grid point over the entire grid, and then you take the smallest delta t over the entire grid. Okay, that's how you apply this. Because in practice, what we will have a speed that varies in x, y, and z, a diffusion coefficient that might be variable. Let's say you have turbulence. Your total diffusivity is going to be affected by turbulence. So you're going to have an effective diffusion coefficient that is different at each grid point, okay, from other grid points. So you have to compute this rule at every grid point and then take the minimum time step across all points and say, okay, this is going to be my next time step. For the problems we did together, we had fixed the diffusion coefficient and fixed the speed. So we can set delta t from the get-go, from the beginning, okay? And that's how we will operate until you get to more realistic problems where you have to adjust your delta t as you move your solution along, okay? Because you might have new things happening in your solution, might drive your delta t down, might drive it up, okay? So you'd have to adjust your delta t according to that. Different schemes, also this is taken straight out of our paper. It's a really neat paper if you wanna look at it. We have a lot of different rules for different combinations. So this was the one I showed you for central advection and central on diffusion. These are the 2 rules. We call them inner rule and outer rule. We explain why in the paper. So essentially, rule 1 is when you are diffusion dominated. Rule 2 is when you are advection dominated. Okay, so that's why you saw the Fourier number less than half show up on the inner rule, because that's diffusion dominated. And Fourier was the condition on diffusion. Then we do it for Runge-Kutta 2, 3, and 4th order. Then what if you do upwind on advection and central on diffusion? Right? So we didn't have that stability. It turns out that there's only a single rule for that condition. And then finally, if you are only doing upwind on the advection equation only, for forward Euler, so FTUS on advection in all dimensions, the sum of Courant numbers needs to be less than 1. Excuse me, I need this rule because we're going to do the 2D advection equation shortly. Okay? Okay, great. Now we talked about stability is out of the way. What I'm after here are actually the 3 pillars of numerical methods. They're called stability, consistency, and convergence. We talked about stability now, so that's that's in our books. Next, we talk about consistency. I have 2 definitions of consistency. We'll read them. A finite difference approximation to a linear continuous PDE is said to be consistent if the truncation error approaches 0 as the time step and grid spacing both approach 0. So as you shrink dt and delta x, your truncation error will go to 0. Or another definition, a numerical scheme is consistent if its discrete operator converges toward the continuous operator. So if your numerical approximation to the derivative actually converges to the true derivative. Okay? Now you might say, like, what the heck? Is there any scheme that violates this? Yes, we're going to see a lot of schemes later that violate the consistency condition. So mathematically, if you take the advection equation with the forward in time, central in space scheme, the truncation error was delta t and delta x squared. And so that approaches to zero as delta t and delta x both approach 0. So the truncation error for the FTCS scheme on advection, keep that in mind. So the FTCS on advection is consistent. The truncation error does go to 0. Okay? An inconsistent scheme, for example, would have this kind of truncation error, and we will see this later once we hit the hyperbolic systems. Truncation error delta t, delta x, and then you have a term that has delta t over delta x. Like, which one is going to go to 0 faster, delta t, delta? It's inconsistent. Your truncation error will never hit 0. Okay. Convergence is the third pillar of numerical methods, and it says that a scheme is convergent if the solution of the finite difference equation goes to the solution of the continuous PDE as you shrink delta t and delta x. And you're like, well, how is that different from the consistency? It is very different. So do not confuse convergence with consistency. And I'm asking you now, can you think of a scheme that is consistent but not convergent? Advection. It is consistent. Truncation error goes to 0. But it doesn't converge. It converges to the wrong solution. It converges to a different solution. So they're different. Consistency and convergence are different. And one does not imply the other. Okay? But here's the theorem that ties those three things together. It's called the Lax-Richtmeier equivalence theorem. So these people developed the foundations of this. Yes? It is consistent with the operators that its truncation error does go to 0. But it's not convergent. It doesn't converge to the solution of the PDE. It converges to another solution. Yeah, so okay? Like consistently is wrong. No, you can't. You're using consistently in a different, yeah, the English vocabulary meaning. That's not, it's not, I see the pun there, but it doesn't, that's not the strict meaning of it, okay? So, the Lax-Richtmeier equivalence theorem ties these three things together. It says a consistent scheme is convergent if and only if it's stable. So if we take a consistent scheme and make sure it's stable, then we guarantee that it's going to converge to the true solution of the PDE. Okay? So that's interesting because convergence apparently is a harder game to get, harder thing to prove. Consistency is easy to prove. Stability is kind of easy to prove, right? You can do these oscillations and whatever von Neumann analysis. Find the conditions. Then if you can, consistency is easy because it's just truncation error. And then if you can prove these two, then you guarantee convergence to the true solution. Okay. Now it's time to grow up. Okay? Let's go to 2 dimensions. Let's get your notebooks. And we will do the 2-dimensional advection equation with FTUS scheme. So with upwinding, you can add diffusion. That's not a problem, but we'll do it because the elephant in the room here is how do we do 2D now? How do we create a grid in 2 dimensions? How do we store the arrays? How do we manipulate them, etc.? So we'll do it for advection. It's easy to understand. With upwind, it is easy as well, and it is stable. For the sum of Courant numbers, it's less than 1. Okay? So this is the equation that we will solve. du by dt is minus some speed in the x direction times du by dx, minus some speed in the y direction times du by dy. So this is advection in x, and this is advection in y. And we will do for a generic initial condition sine omega x times sine omega y times y. So I'm going to have these cells, so because this sine has a frequency omega x in x times a frequency in y. So this is going to combine into like these cells of information that go up to 0 and up and 0. And then we should expect them to just move in time. That's advection. Because the exact solution for this is sine omega x times x minus ct plus sine omega y minus vt, okay? Okay, we will assume that u and v are 0 for simplicity. Once we get coding, we can change those numbers a little bit. And this is the upwind scheme. If u and v and 0 are 0, you're just doing backward differencing. Now you have 2 grid points at point ij on the grid, not just point I. Time is still in the superscript as n. And at point ij, this is saying, the forward in time is saying everything is evaluated at n, okay, and at the old value. And it's saying this is uij at n minus the upwind in x. You're upwinding to I minus 1. And the upwind in y, you're upwinding to j minus 1, right? Because information is moving from left to right, bottom to the top, okay? Yes? Yes, yes, thank you. Yeah, it should be a delta y over here. We'll fix that. And the condition for stability is that the sum of Courant numbers is less than 1. Okay, so that is going to give us the condition on stability. Okay, so how we're going to do this, we're going to create a 2-dimensional grid. It looks like our 1-dimensional grid, and we're going to add ghost points as well, because ghost points are going to help us with periodicity like we did last time. But instead of doing 1 point now, we're going to do an entire plane over here, entire line of points, okay? And we index again with Python from 0. The blue region is our computational domain, and effectively the indexing starts from 1, 1 to nx and y, okay? We're going to have nx points in the x direction and y points in the y direction. Okay, and for a total number of points from 0 to nx plus 1, including the ghost cells, and 0 to ny plus 1 in the y direction. Now, it's like our school of thought when we're dealing with Python, we're probably like finite number of people in the world who approach this in this way, and it is the right way. Okay, and it's hard to be right in this world, so you get a lot of criticism about it, but it is the right way. And I like to align our, so we're obviously going to use NumPy arrays for this. We're going to use two-dimensional NumPy arrays to represent this solution. But I want my NumPy array to be consistent with my Cartesian grid. So I want my indexing, if the NumPy array looks like a matrix with rows and columns, I want my rows to represent the y-axis and the columns to represent the x-axis, okay? Now, Python NumPy arrays stores arrays as rows and then columns. And if you go in 3D, it stores them in hypercolumn and then row. So it goes from z, y, x, or, you know, y and x. So I like to index things as uji rather than uij. So when I go create an array, I'm going to create an array of size ny and x, not nx and y. I created a size ny and x because then it's going to look like exactly like this grid when I print it or when I plot it. Okay? So we will create our arrays. The first index is going to be j, corresponding to the y. The second index is going to be I. So once you do this, it makes everything nice and clean. You're just swapping the indexing. In our discrete formula, we had ij. You can swap them into ji. It doesn't matter, right? But with Python, it eliminates a lot of nightmares. You don't have to think about what is the row, what is the column, what is this, what is that. You know that this indexing, so when I say u5, 3, I know that this is going to be 5 in y and 3 in x. Whereas if you put u3, 5, it's going to be 3 in y and 5 in x. Okay, so just keep that in mind why we do this. Okay. So in other words, our NumPy arrays will be made to mimic the Cartesian grid, the logical Cartesian grid. Now that is going to be super helpful because then I can reason about my NumPy array logically. I can say, give me all the points on this plane, or give me all the points on the left wall. Then I can easily think about it this way, like, okay, all the points on the left wall, I need to go over all y and x equal to 0, for example. Okay, so it simplifies things quite a bit. Clearly, the best example is to do it by hand. So let's go ahead and do that together. get your notebooks up and running. Move your boilerplate if you want. All right, so we will create a new notebook over here. And we'll call it in class 2D advection with FTUS scheme. All right. So we will solve. Again, I'm not going to type much text. 2D linear advection with FTUS scheme. Okay. With your favorite professor signed. Okay. Okay. All right. So let's get our boilerplate. We'll copy them from here. It's nice to have that boilerplate, right? Okay. It's taking a second. There you go. Okay. So where do we start? Let's just declare the number of grid points. Okay. So let's say nx is 21 grid points and y is 21 grid points. Doesn't have to be equal. It's always easy to start with equal grid points so you can get away with errors and mistakes. Okay. Lx, my domain length in the x direction, is 1. And Ly is 1 as well. So this is just a square. Now, I always like to have my coordinate system set up, x and y. Because when I want to plot versus x and y so I can see things nicely and correctly. Okay, rather than plotting versus array indexing. Okay, so let's do that. Create our coordinates. Create coordinates. Okay, x is numpy.linspace from 0 to Lx with nx points. Now, note, I don't need to do ghost points on x and y because I'm only plotting on the interior points. I'm not plotting on ghost points. Ghost points, I reserve them as a temporary thing to help me apply boundary conditions. That's all. Okay, and then y is mp.linspace from 0 to Ly of size ny. And again, if you're in doubt, print it out. You'll see all your numbers. Okay, and dx is, so we can put dx up here. It's x1 minus x0, and dy is y1 minus y0. Okay. Okay. I want to start by plotting the initial condition. Okay. So define initial condition. Omega x, we said our initial condition was sine omega x plus times sine omega y. So omega x is 2 pi and omega y is 4 pi, let's say. Okay. And then my initial condition is lambda xy np dot sine omega x times np dot sine omega y times y. Then what do we do? Let's create a contour plot. This should be a two-dimensional solution, right? Or three-dimensional, if you want to call it. So x, y, and values, right? So it's a surface in space. So we need to be able to plot this solution on the xy plane. And 3D plots, I like contour plots instead, which are a projection of the 3D plots. Okay, so we will do that. Okay, so let me see how, for my 3D solution, maybe we could do, okay, u0 of x, y. Okay, it does something. Let's see if we can do a contour. plt dot contour xy u0 of xy. It threw an error. Whoa, look at that. Input Z must be 2D, not 1D. Oh, of course. Our X and Y values just represented one line on the grid, not the entire grid. I need a 2D representation of all the X values and a 2D representation of all the Y values. So in other words, if I were to go to my grid over here, what we created, we just created this line and that line. No, what we need all of these lines for X and all of these lines for Y. Does that make sense? So I need to have a true two-dimensional representation of X and Y. What I have now is simply one line of X and one line of Y. Luckily, Python has a built-in feature that does that for you, and it's called mesh grid. So now we say, okay, create the 2D grid. Okay. And then we say, we call something called an np.meshGrid, and you simply give it X and Y, and it will return two-dimensional representations of X and Y. I call them XX and YY, because I'm very creative with my naming conventions. So XX and YY are the 2D representations of X and Y. All right? If you don't believe me, let's plot them. A very simple way to plot this is plt.imShow, which shows a matrix as a colored image. XX. Okay, so notice now, this is a representation of my X. X is fixed for all Y values. Then X is increased for all Y values. Then X is increased all the way to the end. So you get the same X value, but for all Ys. So it's taking that line of X and repeating it n Y times. Make sense? We do the same also for Y. So for Y, if you do plt.imShow YY, it's the same thing. Y is constant. It's the same Y value, but for all X. And then it repeats it. Okay? So now, oh, yeah. Sorry. Okay, here, right? Yeah. So what mesh grid is doing, it's reproducing your X line axis and Y times, and it's reproducing your Y axis, your Y coordinate, and X times. Now you need that, and then you pass that to your two-dimensional function, and then you get a true surface. Because the surface needs to be plotted versus X and Y. You need two-dimensional arrays for those, okay? Yeah.
For some reason, I have WX and WY in here in that lambda function. Where did that go?
Oh, down here.
Did we get rid of that?
Nope, they're down here. We didn't. So now instead of passing X and Y to my contour plot, I need to pass XX and YY. And now see what happens. Nothing happens. Oh, YY. Sorry, YY. Now see what happens. So I'm going to do contour F, filled contour. Now that is more interesting. I have wave number 2, so 2 cells in the X direction and 4 cells in the Y direction, as we expected, right? Now this is a cool, interesting situation because it's a surface positive and negative, and you could put the color bar here, plt.colorbar, and you can see the values from -1 to 1. So these are troughs and peaks, right, that are going up and down. We're going to advect all of that, okay? And you can change your frequency as you please, and you'll have like 2 cells in each direction, which is fine. You can add more points to make it look nicer. 33 points. Okay? That's a good, nice initial condition. Okay, let me scroll up in case you're still catching up. Yes?
So the function, the contour F, that's actually taking
Yes. Yeah, as you saw here. So if you do xx.shape, you get 33 by 33. It is a two-dimensional array. And it's plotting u0 at each combination of x and y. So it takes xx and yy and lays them on top of each other. It takes each point, plots a value, projects it to make a color, makes a contour. Okay? And if you remove the f, then they become contour lines, so they're not filled anymore. F will fill them. Okay. Are we there?
I mean, mine doesn't look as cool as yours, but yeah.
All right. So now let's actually get to set up the problem. We set up kind of the boilerplate stuff and the problem setup. We define the x velocity as 1, and then the y velocity v as 1. And let's go ahead and use our stability conditions. So if you remember stability conditions, if you remember, we needed the sum of Courant numbers to be less than or equal to 1. Agreed? So now what is the sum of the Courant numbers? Was u in absolute value, delta t over delta x, plus v delta t over delta y. So you can pull delta t out, okay, and then you get 1, and then minus all of that, all of the other ones, okay? Or sorry, 1 over u over delta x plus v over delta y. So then if you solve this equation, sum of Courant numbers, you get dt is equal 1 over the absolute value of u over dx plus absolute value of v over dy. Okay. Now, you know, I like a little safety factor here. So instead of 1, maybe we put 0.95. Okay? So that's the condition that it tells us. Then I say dt is just take 95% of that. Okay? Just rescale it a little bit. Okay? Now, I'm starting from t equals 0. T end is equal to 2 seconds, let's say. And now I define my Courant x and Courant y because I know I'm going to have u dt over dx and v dt over dy in the formula, right? So I'm going to define Courant x, and this is a signed value in this case, not with the absolute value, because you need to advect in the correct direction, right? So u times dt over dx, and Courant y, let's capitalize his name, v times dt over dy. Right? Give you a second to catch up. So the sum of the Courant numbers is going to give you delta t times, in parentheses, u over dx plus v over dy less than or equal to 1. Then delta t is less than or equal to 1 over all of that. So that's how we got this. It's really nice to have a guideline for time step selection, seriously, because then you don't have to guess anything. Now, time step selection goes beyond that. If you know your physics, you know your time scales that you want to resolve, then you choose a time step according to the time scale that you want to resolve. In a turbulent flow where you might have eddies that are on the order of milliseconds, they're spinning, you want to capture those, then you set your time step to that number. And that will obviously be smaller than the stability time step, perhaps. So it will still satisfy stability. Okay, are we in sync? All right, let's develop our solution now. Set up solution arrays. So I want to store everything in sol. Again, very creative name. And let's declare our solution array, which is just u is equal numpy.zeros And again, I'm going to index in ny, in y, and x. I'm going to follow that nomenclature. Okay? So ny plus 2 for the 2 ghost cells, and nx plus 2 for the other 2 ghost cells. Now, on all the interior points, I want to initialize the initial condition. So again, same thing with 1D. The interior points go from 1 to -1 with slicing. In this case, we're doing it in 2 dimensions, in y and x directions. And that is equal to u0, xx, yy. Okay? So if you want a sanity check, you can do a, you can just plt.imshow of u. You're going to get zeros on the ghost cells, right? Because we got nothing in the ghost cells. You see that green, only solid green on the boundaries? Those are the ghost cells. There's nothing in there. We only filled in the initial condition at the interior points. Okay? All right. Similar to what we did last time, we need to set periodic conditions on the initial condition as well, so that we can just run our loop and not worry about what's at the boundary. Okay? All right. So how is this going to happen? We're going to go after left wall, right wall, top wall, bottom wall. Okay? Or we also call those x minus, x plus, y minus, and y plus. So the x minus face is the left wall. The x plus face is the right wall. The y minus face is the bottom face, which is the bottom wall. The y plus face is the top wall. Just a nomenclature convention. Okay. So let's start with this. Left face, or x minus face. Okay. So now with slicing, remember our periodicity. On the left ghost point, we take the third one. Where is that slide? Let me get that slide for periodicity. Just 1 second. Yes. So remember, with periodicity, u0 is u minus 3, and u minus 1 is u2. Now we're going to do this over in the x direction, so over the entire face here. We're going to inherit this entire face. We're going to move it here. And this entire face, we're going to move it here, but also in y. You do it in x, and then you swap the index, the slicing in y, and you're done. Okay? So keep this in mind. In 1D, this is what we had to do. Okay, so I'm going to copy that and go here. In 1D, we had to do this. Okay? In 1D, we had to do that. So now, what is the left face? What is the indexing on the left face? Now, remember, I'm indexing in J and then I. So if I want the left face, I want all the J values. So I start with all the J values, semicolon, right? All the J values. Okay? 0. Right? So that gives me all the set of points at the left face. Okay? In the ghost cell. And that's equal to all the points in the y direction at -3, right? So that's u0 equal -3. You do it for one face, you're good to go. Then we do right face, or x plus face, and that's going to tell us u minus 1 equal u2. I just copy and paste this. And that's going to be u minus 1, whoops, equal to u2. So what this is saying is, on the right face, all the points in y at x equal -1, or I equal -1, that's the right plane, they're equal to the third set of points from the left-hand side. Okay? You repeat bottom face or y minus face, bottom. You take this and you swap the indexing. You say 0 semicolon and -3 semicolon. Why? The y minus face is taking all the x points. So my second index in the array is going to be the semicolon, 0. So the first, set of points in the y-axis, which is the ghost cells, is inheriting the points from that third one. So let's go back to the 2D grid. So what we just did, we're saying this guy is going to inherit all the points from this guy. And then we're going to do this guy is going to inherit the points from this guy. Okay? Yes, that bottom one. And then y plus face, top face. Okay, we're out of time, but let's finish this. If you have 10 minutes, we can finish it in 10 minutes. And then finally, the y plus face, you take that x thing and you just swap the indexing. That's what's so nice about slicing. And then sol.append u. We have that initial, we now have that initial condition stored in our solution variable, right? Now we begin our time advance loop. While t less than t end, un is the last solution, so sol minus 1. U new, or un plus 1, is equal un dot copy. So I'm going to make a copy of that so I don't alter it. Okay? And then we implement our advection scheme. U new on the interior, only on the interior. Okay, so because we're going to reach out of the interior, right? So I'm only going to fill in the interior points. From 1 to minus 1, 1 to minus 1, okay, is un from 1 to minus 1, 1 to minus 1. So over the last couple of days, I was trying to figure out if we can store this indexing in a variable. So you could say u interior points, u left wall, u right, u left. You can store only one pair at a time with a function called slice, but it's like it adds more complexity to it, so it's just easier to do it this way. If you know of a way of doing like 2 3-dimensional slicing, storing them in variables, that would be very effective, because then you store a variable for interior points, store a variable for left wall, right wall, and then you can just reuse that very effectively. Anyway, let's do this the hard way now. All right, so now in the x direction, we're going to upwind, okay, to the left. So it's going to be ui minus 1. All right, so we have minus u delta t over delta x, which is courant x, times, okay, what is ui is simply the interior point, 1 to minus 1, okay, minus, in the x direction, the points to the left. So I'm going to take all the points in the y direction interior. Okay, remember, the first index is the y index. And then I'm going to take the points to the left. So this will be minus 2, just like we did in the advection 1D case. Okay? So if I zoom out a little bit here. And same thing for the y case. So v delta t over delta y. So that's courant y. I need to do a multiplication here. Times, again, now here we're upwinding to the bottom, right? Because the flow is going bottom to the top. So it's going to be uj minus 1. X will be untouched. Okay, so I know that there will be something here. So this will be uj, 1 minus 1. And x will be untouched, so 1 minus 1. Minus the j minus 1 values. So un, what are the j minus 1 values? They're starting from the beginning all the way to minus 2, right? And then all the x values, 1 to minus 1. I don't know why I ran it. Shouldn't have ran it. It's taking a long time. Let me restart this. Okay. Okay. Now I want to set the boundary conditions again. All I have to do is just take this and copy and paste it and do it on unew. Okay? Instead of u, I just do unew. Now imagine doing for loops for those. Yeah, no for loops for me.
Did you on the CRY times that is a UN square on the first one?
Yes, thanks, Brent. Thank you. Yep. That's why it wasn't running. All right, and then we say sol.append unew and advance in time. All right, do you think it's going to run? Yes, it ran. Okay, that was pretty fast. Okay. Can we plot it? Can we animate it? The annoying thing about these things is that you need to animate to see what's going on, and then you make plots out of your solution, right? So we have to have our plotting capability, our animation capability. Okay, now this is I built this one on top of the other one. You can use the other one you have, or just implement this one, because this one now is doing it on contours, okay? So I'm creating a figure size 6.1, face color white, whatever, and then I'm creating my own levels for the contour from -1. Remember here now, I don't have a plot.y limit. I have contour levels. And I'm going to anchor the contour levels from -1 to 1, because that's where my initial condition is, -1 to 1, agreed? And then that will fix your color map, and then you can see if there's any diffusion going on, your values are going to go below those limits. Don't change the limit as you run your solution, all right? And yeah, you just run this. Let me just run it for you. It'll make you happy. CM is undefined. Oh, yes, I need to import the color map thing. Okay, add this to your boilerplate. From matplotlib, import CM. CM is color map. Okay, so we'll run this again. Import CM. From matplotlib, import CM. It's right here. Just CM. Okay, I will send you this so you can implement it. But okay, this looks correct, at least the initial condition. All right. What do we expect to see? Okay.
I would imagine it would become eventually closer to all one color.
Okay, why?
Diffusion.
Where is the fusion coming from?
Oh, sorry, the advection. Sorry, but it's from the truncation error.
From the?
From the truncation error.
Okay, so from the upwinding, because we said upwinding is diffusive. We did upwinding in both directions, so we expect it to diffuse, right? So we're going to see diffusion. So eventually that color is just going to be smooshed. We're going to have one color, right? Okay, how can you predict the direction of diffusion? Okay, so these are cells, right? Are they going to diffuse? Are they going to remain cells and diffuse nicely this way? Are they going to turn into blobs in this direction, that direction? What do you think is going to happen? Pardon me? Hot and cold, but they're going to diffuse in place, so they'll retain their shape. You don't think so? What's going to happen to them?
Maybe they'll distort.
Why?
The direction of the advection.
Along the direction of advection, because it's like tearing them apart, right? That's what, okay. Okay. or you're all wrong. You're partially right. But you'll be surprised that they're going to actually distort perpendicular to the direction of motion. Okay? So let's see that. Okay. They're diffusing, and look at that. They're distorting opposite, perpendicular to the direction of motion. And in your homework assignment, the third one, you will prove that with the modified equation. What happens in this case, in this very particular case for two-dimensional advection, you will get a cross diffusion term. You get a diffusion term perpendicular to whatever direction of motion I put. Whatever angle I put it, you're always going to get diffusion perpendicular to that in the xy essentially direction. So you get du by dx dy. You get a term like that, which is diffusion occurring in a perpendicular direction. So this is what happens. Pretty neat, right? But there is diffusing. So, you know, that's the price you pay for stability for upwinding.